See, I'm gonna forget everything. Mostly. And then math, we have our first exam on the 15th.
Okay, howdy everyone, we'll get started. So hopefully this works better than last week. And this is what I did for last semester, but essentially I'll be writing everything on my iPad and then you should be able to see it up here. So hopefully that works. But welcome to another week. If you weren't here last week, I do my office hours review sessions a little differently. I just kind of feed your questions, take your questions, and I'll either give you practice problems or just kind of use this hour to practice chemistry, and then we'll ask and we'll practice what questions you have. So feel free to ask anything. This hour is yours. So anything we want to discuss first?
I forgot how the question's worded, or it's like,
I had a general question.
Yeah, absolutely.
Since tonight is for some classes, we have the quiz due tonight. And what would you recommend to study?
So any of your homework questions should be very reflective of what the quiz is. I think we have Altimos and Altman in here. So if you're in Altimos, do we think that that's a valid?
That's a valid thing. And what I did is, I had to do it for a class, so I kind of double dipped, but I used ChatGPT to make me a study guide. I know it sounds kind of stupid, but I had to do it for a class. So I was like, why not try it? I used it to make me a study guide, and it's something that I did, something that I didn't understand. Something I didn't understand. I would literally make it explain it to me. And I literally put it in there. I'd be like, explain it to me like I'm a 6-year-old and I don't know anything. And then it would like break it down really simply for me. But do that with your like homework questions that you don't understand. Maybe is what I would say.
Yeah.
Other than coming in,
Yeah.
we didn't have this yet when we did our quiz today.
Yep. So I think that right, that's a great way, just different ways that you can have the questions breaking down for you. If you really understand a question and it's just like, okay, I just need to practice it in order to understand it. There's a ton of practice questions online that you can look up. So if you're just really struggling with percent composition, if you look up percent composition problems, answers, then you should be able to get a worksheet that has questions and answers written out for you that you can study from as well. They won't be exactly like the quiz, but they would at least just give you more practice and make you more aware of what that question could be asked like. And I think that's a really good thing. And then any of the practice questions in your slides are always a good starting point as well.
Okay.
Yep.
Thank you.
Absolutely. Any other questions?
Can you do percent?
A percent composition question? Yeah, absolutely. So I think I have one. And then I also we'll post this after, but I do have a practice question for percent composition that we can do. I had a comment last semester that was a little messy, so. Okay, so let's try number 6. So question 6 is asking for what is the mass of NH4OH, which is ammonium hydroxide. So let's kind of talk through percent composition, what that means. So if we are trying to solve this question, when we say percent composition, what are we looking for? Like, can someone break that down into different terms of percent composition? Perfect, right? Percent composition is just telling us how much of each element is in our overall compound, right? So how many or I guess we're looking for hydrogen here, but how many different percent compositions could we find from ammonium hydroxide? We could find 3. Why? Because we could have nitrogen, we could have hydrogen, and we can have oxygen, right? So there's 3 different percent compositions we could find, and those 3 percentages should equal our entire compound. So we need a percent or looking for a part of the whole, right? Or a percent. So if we're looking for the mass percent of hydrogen, what do we need to know about hydrogen? Its mass. Yep. Does anyone know hydrogen's molar mass? Yep, we can call it, I usually call hydrogen 1.01. And where do we find hydrogen's molar mass? periodic table. And what else do we need to know in order to find percent composition? The total mass, right? So for our total mass, how many nitrogens do we have? 1, and that's going to be 14.01. How many hydrogens do we have? 5. Yep, I picked this one just so you had to do a little bit of math. So we have the 4 from the ammonia, but we also have the 1 from the hydroxide. So there's 5 total hydrogens in ammonia hydroxide. So we're going to have 5 times 1.01. And how many oxygens do we have? Just the 1. So we'll have 1 times 16.00. My calculator today.
And you're getting masses from the.
Yep. And if you're in Dr. Altamos's classes, I know we have the group me, but this, so as someone asked about the periodic table, not working on OWL, but I always have P table like literally never closed on my tabs on my computer. And this is P table, and this I think is just very informative. You'll use a lot of this stuff later on in chemistry, the more you delve into this semester, and then if you have to go into orgo or anything, you'll use it a lot. So like this chart on this side is very, very helpful. And then it's just very nicely color coded. So if you don't have, if something's not working, the P table is always a great option. But in this corner here, we do have carbon, nitrogen, oxygen, right? So we're using nitrogen and oxygen here, and then hydrogen's over here on the left. Okay, so I wanted to recommend P table. Okay. So did anyone get the total mass of ammonium hydroxide? $25.06, 35. Okay, great. So if we're going to find the percent mass of hydrogen, what else do we need to do? Yep, perfect. So we're going to do percent composition or percent mass of hydrogen is going to be our total hydrogen. So what's going to be our total hydrogen mass?
5.
Yep, 5 times the 1 of hydrogen. So it's 1.01 divided by our total. Okay. This ends up as 5.05 divided by 35.06. What does that come out to be? And is that in a percent? Nope. So then we multiply by 100 and we get 14.4%. Does that make sense how we found hydrogen? Can someone give me a way that we could check our answer? Yeah, yep. So I think what you're saying is like we could find the percent of oxygen and we could find the percent of nitrogen. If those add up to be whatever, what is that? 86-ish%, right? Then that means that that other 14% is going to be made up of the hydrogen that we already found, right? So you can find the other mass percents of the elements in your compound and make sure they all add up to 100. If they all add up to 100, then you're probably on the right track. You did your math correctly. But if you get something that's like 200% or you get something closer to 80%, then you probably messed up somewhere or you forgot a component or a number of one of the elements in there. Okay, so maybe you forgot to add in that 5th hydrogen, right? So your percent's going to be a little bit lower than you expected. But in this case, I think this is correct. So that would be good to go. Does that make sense how we could check our answer? Yes. Does that help with percent composition? Yes. What other questions do we have? Did you find your question that you wanted?
I think it was that. I saw it, when I like encountered it, I thought it was like.
Okay.
What about, the one where it's like, you're given like masses and you're trying to figure out like.
The empirical
The
formula.
empirical.
Yep,
Yeah,
yep.
yeah, that was, I was like trying to, I was like, I know there's some specific word for it, I just can't remember right now.
Yep. So that would be question 7 here, but let's talk about empirical formula first. So what does it mean to be an empirical formula? Yep. So this is your chemical formula. In its smallest whole numbers. Okay, so an example that we used in class was glucose, which is not the G, C6H12O6. Would that be glucose's empirical formula? No, what is this called?
Isn't that sugar?
The molecular formula. Yep. And it is sugar. Right, this would be glucose's molecular formula. What would its empirical formula be? Mhm. Yep. Okay, so we see that we still have that ratio where for every carbon and oxygen, we have 2 hydrogen molecules for that CH2O. But glucose, when we're talking about its molecular formula, we're saying, okay, this is the actual chemical formula with as many carbons, as many hydrogens, as many oxygens as possible. Okay, so things can have the same molecular, the same empirical formula, but different molecular formulas. Right, so you can boil it down where sometimes maybe something is C4H8O4, right? Whatever this compound may be has a different molecular formula than glucose, but has the same empirical formula as glucose. Do we see the difference between those and what would happen? Okay. So to tell the difference between how a lot of the questions are going to be asked between empirical and molecular formula is that you're always going to find the empirical formula first, and then you're going to be given the molar mass. The molar mass of something would be for the molecular formula. So if you have something where, let's say its empirical formula is CH2. What would the molar mass of CH2 be? 14. Yep, it's about 14. But if we found this molecular formula and we said that the molecular formula for whatever this compound was about 112. How would we find what the actual molecular formula is? So when we're looking at the empirical, we know that carbon is going to be 12, and we know that hydrogen is going to be 1. We have 2 of those. So we're just using the periodic table to sum the molar masses of both of those. Yep. Okay, and then I heard it over here, right? In order to find the molecular formula, we're going to take 112 and divide it by 14. And this we get as 8. Right, so we're saying that we have 8 times as many CH2s as we do in the empirical formula for the molecular formula. So you're going to multiply all those subscripts by 8. So your chemical formula or your molecular formula would be C8H16. Because we took 1 times 8 and 2 times 8. Does that make sense how we found the molecular formula from the empirical formula? Yep. What questions do we have on this? All right, let's try a practice question. Okay, so we have question 7. What is the empirical formula of a compound that contains 81.82 grams of carbon and 18.18 grams of hydrogen? What is the molecular formula if the molecular weight of the compound is 78 grams? Okay, so we can do this together and we'll walk through it. If you feel confident, feel free to work ahead. And I'll give you all a second to just kind of copy it down before I start talking. Everyone read that up there too. All right, so we're given that our compound is just carbon and hydrogen. We have 81.82 grams of carbon and 18.18 grams of hydrogen. So what's the first thing we need to do in order to solve this question?
Figure out what.
What were you gonna say? Perfect, right? So they're saying the same thing. We don't really like to work in grams in chemistry. We really do like to work in moles. So we want to convert our 2 grams that we have into molar units. So for our carbon, we have 81.82 grams. We're going to divide this by 12 because for every 1 mole of carbon, it's 12.01 grams of carbon. And that is molar mass directly off of the periodic table. And when we get this, and we convert this to moles, we get 6.8 moles of carbon. We can do the same thing for hydrogen. But this time we're going to divide by 1.01 grams because we just said from the last question that that's the molecular weight of hydrogen. So now that both of our components of carbon and hydrogen are in moles, what do we do next? Not yet, there's one more step.
Divide by the smallest.
Perfect, right? We need to convert this into the smallest ratio, right? Or the smallest, divide by the smallest mole. So we're going to take 6.08 and divide by both of those. So carbon ends up becoming 1. Get 2.647. Are these 2 whole numbers that we can put in an empirical formula?
No.
No, what do we have to do instead?
No.
We could round, or what's something else? Yes, so for 2.64, I would say that's a little bit closer to your 2.5 range rather than your 3 range. So in this case, we're gonna, if we're at 2, let's say we're at 2.5, what would we have to do? Multiply by 2. So let's multiply by 2 here. Right, this would be a little off, but we'll pretend it's 2.5. Let's just say this is 2.1-ish. It's a little off, but it's fine. Okay, so if that's at 2 and 5, what do we do now? Yep, you can round down. So if that's at 5.1, this would become 5. Okay, so that's kind of what both professors talked about, right? If you're anywhere, if you're like 0.1 to 0.2, I would say round down to your nearest whole number. If you get 0.25, that's going to be multiplied by 4. If you get 0.33, what are we going to multiply by that there? That would be 3. If we have 0.5, we said that's multiplied by 2. And what if we have 0.67? This one could also be a 3, right? Because this is 2/3 of a decimal point. So you can multiply by 3, and that would also give you a whole number. So in this case, this one, right, this is round. This one's times 4, this one's times 3, this one's times 2, and this one is times 3. Anything else about that, you could probably just round up. And those should be pretty clear. If they're not clear, then just ask someone during an exam. But for your quizzes, at least it should be pretty clear. Okay, so how do we write once we have 2 and 5? What do we do from there? Yep, now they become the subscripts. So we can say C2H5. What is our molecular weight for our empirical formula? And how'd you get that? Sorry, for like C2H5, what would be our molecular formula? Yep, perfect. So we did some mental math. This was 12.01 times 2 plus 5 times 1.01. This is 29. It's a little weird on my math, but that's fine. Let's do. Let's change 78 to 58 for sake of math. So if 58 is our molecular formula, what's going to be is our molecular weight for our molecular formula? What's going to be our overall compound? Beautiful.
Yeah.
Yep. Yep, so if we took 58 divided by 29, we get 2 times. So that means that our molecular formula is 2 times as heavy as our empirical formula. So we need to multiply everything by 2. What questions do we have on this type of question? Okay, does that help break that down a little bit more? Okay. Have we seen anything with like combustion analysis type questions yet? No? Okay, we'll save that for later. Wasn't sure if your homework dealt into that yet, but I think that comes in a couple later chapters. Alrighty. What other questions? Do we want to practice another one of those, or just do another type of question? Feel comfortable?
One I saw was like, it was how many atoms of, it was a compound, and it was asking about atoms of like a certain amount of grams of the substance.
Okay, we can definitely do one of those. So when we talk about atoms, this can be atoms, molecules, anything like that. What number comes into mind? Avogadro's number. What is Avogadro's number? Good. Okay, this is Avogadro's number. Know it, love it, celebrate it on October 23rd. But this is like your favorite number when it comes to general chemistry right now. Avogadro's number is very similar to saying like you have a dozen of something, right? This is saying this is equal to 1 mole. If you have a dozen of something, then you have 12 of it. If you have a mole of something, you have 6.02 times 10 to the 23rd of it. Okay, so if you have a mole of cakes, you have a lot of cakes. Does that make sense of what that is? It's not 6.02 times 10 to the 23 moles is equal to something. 1 mole is equal to this value. Does that make sense? Yes, okay. So when we talk about grams and atoms of something, if we're looking at, we'll just stick with ammonia hydroxide. If we're sticking with ammonia hydroxide, if we have 12.6 grams of this, I want to know how many atoms of oxygen are in our compound. Is there a conversion that gets us directly from grams to atoms? No, what's our roadblock in between it? That's the mole, right? So if we're starting with 12.6 grams of ammonium hydroxide, how do we get out of that grams? What do we need to use?
Like, how do you know when
So whenever you have a starting material, so that 12.6 grams, you can always think of that as like the top of your fraction. So that's always going to be starting. If you're trying to get rid of that, then you always want to put what you're getting rid of on the bottom. Yep, to divide it out. Perfect. So what are we going to use in our train tracks? So 1 mole of ammonium hydroxide is equal to what? The molecular weight of ammonium hydroxide. I think we said, thank you.
During like a test or something, do we just like look that up? Like,
Yep. Yeah, you can always look up the molecular formula. It'll either be given to you in the question, or you can always like look it up by doing the math on your periodic table. So you say, okay, I have 1 nitrogen, so that's 14. I have 5 hydrogen, so that's 5. Then I have 1 oxygen, so that's 16. Yep. Okay, so now that would cancel out our grams. Does that get us to atoms of oxygen? No. So what do we have to do now? Yep. So we can use Avogadro's number, but let's say, so I'm going to say this is moles of NH4OH. We're looking for moles of oxygen. So kind of how we ended class today, if you're in Dr. Altamos's class, we said that in calcium chloride, we had to multiply the concentration by 2, right? So for every 1 mole of NH4OH, how many moles of oxygen do we have? Just the 1, right? So if we were talking about that concentration of something, we would have the same concentration of our ammonium hydroxide as we do of the oxygen. So this would be 1 mole of oxygen. Now that we're in 1 mole of oxygen, what can we use to get to atoms of oxygen? Now we can use Avogadro's number. So we have 1 mole on the bottom, right? Because 1 mole is equal to 6.02 times 10 to the 23 atoms
and
of oxygen.
if there was, let's say this was a different formula and there were 3
Mhm.
oxygen, you would put 3 moles.
Yes, right?
Okay.
Yep,
okay.
so if we were saying, if we wanted hydrogen atoms, right, we would still do the same thing. That beginning point's still the same. But now for every 1 mole of ammonium hydroxide, we have 5 moles of hydrogen. Okay, so then for every for every 1 mole of hydrogen, we have that many atoms of hydrogen. Yep. Yes, yep. So you could also, right, just multiply it by 5. If you understand that where like 1 mole of oxygen and 1 mole is in 1 mole of the ammonium hydroxide, feel free to just use Avogadro's number without that middle step. But sometimes visually to see it, that's how you would like cancel your units directly in order to get to the hydrogen atoms or the oxygen atoms here. Yep. I don't know what this number is of how many atoms we have. Should we have more or less than a mole of oxygen? Of oxygen. Like if, so for every 1 mole, we have 6.02 times 10 to the 23. So should our answer be more, equal to, or less than 6.02 times 10 to the 23? So for every 1 mole, we have 6.02 times 10 to the 23 atoms. So should our answer for the number of oxygen atoms, should that be less than, greater than, or equal to 6.02 times 10 to the 23? Why? I like the way you think, but that's not the reason why it should be less. Okay, and why does that matter?
Because you're dividing, like math, it should be.
Right, so we said that for every 1 mole of our ammonium hydroxide, we have 1 mole of oxygen. At our starting material, we have 12.6 moles of ammonium hydroxide. But what's the molecular weight of ammonium hydroxide? Is it greater than or less than the 12.06? It's greater than. So you are already starting with less than a mole of ammonium hydroxide. So your oxygen atoms should also end up as less than a mole because you are starting with less, and those are going to be equal values of 1 to 1. Does that make sense why it should be less? Right, so if you're always looking at what you're starting with and what that molecular weight is, if you see that your molecular weight is less than something and it's only one of those atoms in there, then you should expect your answer to also be less. If you get something that's greater than the 6.02 times 10 to the 23, that should trigger something that say, okay, I might have maybe multiplied instead of divided by something. That'll push you into the direction. What about our hydrogen atoms? What do we think there? That should also be a little bit less than, yep. At least I think I should, if that math by the 5 works out to be as it should, but that one might end up more. But you can definitely tell with the 1 to 1. Okay, so you can find those numbers on your own, but this number should be 5 times. Whatever that comes out to be. So I think your hydrogen atom should end up as greater than a mole. Just 12 times 5 will be greater than 35. Hey, does that help with your question? I do think I have a couple of those problems in here. The first bit of this, is just talking about atoms and moles directly, and then you do your Aggie ring, which is fun. So those first four are kind of those conversions between moles and grams of atoms. Okay, what other questions do we have? Yeah. Yep. Absolutely, yep. So when we talk about percent abundance, what does percent abundance tell us at the end of the day? Yep, so let's talk about like all of your isotopes, and in the overall, you're gonna get the average atomic mass of your compound or of your element.
Percent abundance, the same as percent composition.
No, so those are different. So percent abundance is looking at your different isotopes. So let's say something like chlorine has chlorine 35 and chlorine 37. You can find the percent abundance of each of those isotopes.
Okay.
Okay, and then percent composition is looking at a whole compound and the specific elements within the compound. Okay, it might make a little bit more sense after we do the problem and talk about it a little bit. We can show the difference between the two. Okay, but percent abundance will tell you the average atomic mass of element. Okay, so let's stick with chlorine for this one. So I want to know so I don't know, what is the percent abundance of each isotope if chlorine has two isotopes, chlorine 35 and chlorine 37? So how would we solve this problem? Yep, and where can we find that? Yep, so we can use that from the periodic table. So looking at this, the average atomic mass of chlorine is 35.45. So what do we think should be more abundant, chlorine 35 or chlorine 37? Why?
Because it's closer to the.
Good, so the right person, perfect. So for your percent abundance, this is a relative or a weighted average. So whatever is the most abundant will be the closest to that average atomic mass because it's going to have the most weight over that average atomic mass. So since 35.45 is closer to 35 over 37, we're expecting a more abundance of that element the isotope 35 over the isotope 37. So once we have our average atomic mass, what do we do from here? Yeah, perfect. So we know that we have two elements or two isotopes for our element. So whatever the percent of one would be, the percent of the other is going to be 1 minus what we don't know. So 35.45 is going to be our average atomic mass. And we know that chlorine 35 has an average atomic or has an atomic weight of 35. Do we know what percentage chlorine 35 makes up? No, so that becomes X. This is a weighted average, and so you're going to add the percentage of chlorine 37 times its percent. In this case, since we don't know what 37 is, this is going to be 1 minus X. Because element or isotope 35 will make up X percentage. And whatever is not made up by isotope 35 will be made up by isotope 37. So those two together should come up to add to 100%. Okay, and then this just becomes an algebra question from here. So you can solve this, we have 35.45. This becomes 35x plus 37 minus 37x. I do prefer my x's to be positive, so I would move this to one side. Say that 2x is equal to 1.55. You can then divide by x or by 2 to get x by itself. And then does that tell us the percent of our isotope?
No.
Nope. Again, we also need to multiply it by 100. So we get 77.5%. And which one is that for? Yep, for 35, right? So this is chlorine 35 is 77.5%. So how much is chlorine 37? Mm-hmm. Does that match our prediction before we even started the question? Yeah, it does. Okay, so that's probably one of the harder questions. You do have some where you get like 3 or 4 isotopes, but you would either know most of the percentages and you can just solve for what's ever remaining. Or if you're having 3 isotopes and you need to find what the other 2 are, you'd be given at least 1. So then the rest of it would be like 0.8 minus X or something like that. But this is usually how hard it gets. Yep. Yeah, right. So basically it's just saying that all of this is chlorine 35.45. So this, I guess to scale, right? This would be 35 and this would be chlorine 37. So the percentage of chlorine 35 is that much. And in order to get the entire percentage, you need to take whatever chlorine 35 is, 1 minus whatever that percentage is. Yep. So if it was just asking for what's the percent abundance of chlorine 37, then you could put X as chlorine 37 there. Yep. So you're looking at parts of the whole for both of them. What other questions do we have?
What unit are subscripts of things?
I believe we just started talking about that today. So I think that's like unit 3.
Yeah, like what is like the unit? Like if you were looking at it and you're like,
Oh, like C6H12O6.
like,
Okay.
without an item, or is it-
Yep. So yep. So this can kind of be what you want it to be. I would think in moles. So you can say, okay, I have 6 moles of carbon, 12 moles of hydrogen, 6 moles of oxygen. But you could also think of it as like, okay, I have 6 atoms of carbon and 6 atoms of oxygen, and then 12 atoms of hydrogen. But that I just did Avogadro's conversion in order to think of that in those 2 separate ways, right? Because we looked at moles and then we looked at atoms. So I would say probably moles first, because that's easiest to work in over atoms. And then if you do need to work in atoms, then you can just use Avogadro's number to look at it that way. Does that help a little bit? Yes.
Just say in one molecule of that, there'd be 6 moles of carbon.
Yes. Yep. So for every 1 mole of C6H12O6, you have 6 moles of carbon.
Last week you went through a polyatomic compounds. Or
Mhm.
polyatomic. I forgot how they were called, but you went through those, and I saw the video, but I was a little bit confused on. You divide like chlorine and, sorry, I have it here, like sodium on
Mhm.
one side, and then oxygen and sulfur on the other.
Yep.
How do you determine like the charge of two atoms compared to the other one?
Good. So that comes from the periodic table a bit. Let's see if P table comes up again. So when we're looking at the periodic table, when we're looking at like lithium and nitrogen in that first like brown column over all the way on the left, or sorry, sodium, lithium and sodium and potassium. Those are all going to form a +1 ion because they're a metal and they're in your first row. Okay, and then you can see at the top, right, you can see the 1 through 18 going across. So in that first row, that's going to be everything that makes a +1 charge. In the one right next to it, in that lighter brown yellowish color, you have beryllium, magnesium, calcium. Those are all going to be a +2 charge. And again, you see that 2 up top telling you 2. Those are easy for the metals, and for those first 2 columns. For that middle section where that maroon color is, that's going to be your transition metals, and that's where you get a little bit different, where you need to start using, like maybe it's +2 sometimes, maybe it's +3 sometimes. So your transition metals don't usually have a set state at which they form a positive cation. But for your nonmetals, when you look at fluorine, chlorine, and bromine, all in that row 17, those are all 1 away from your noble gases in 18. So they were always going to form a -1 charge because they're always going to gain an extra electron. And since electrons are negative, it'll give them an extra negative charge. Okay, so if fluorine and chlorine are all -1, what do you think oxygen's going to be? It was going to be -2, right? Because it's 2 rows away from being a noble gas. So it needs to gain 2 electrons in order to have its same shell as a noble gas. That'll make a little bit more sense a little bit later on in the semester. But for right now, say you want to get to 18, you need to move 2 rows over, so it needs to gain 2 electrons. So that's going to make it a -2 charge.
And if you were to, when you have polyatomics, and for example, you have on one side one, and you have on one side I forgot what Na was, but
Sodium, yep.
sodium, and on the other side you have a sulfur and oxygen. And then that sulfur and oxygen combined have like a specific charge.
Yep.
How do you find that charge?
So that's good. So for any of your polyatomic ions, they will be given to you on your chart for either an exam or a quiz. Like it'll be as part of your reference material. So usually on your exams, when those are paper, it'll probably be your periodic table on the front and then your polyatomic ion chart on the back. So in your chart, it'll say, you know, SO3 2-, and then it'll say sulfite. Like that. Okay. And so that'll, and then underneath it will say SO4 2-, and that'll be sulfate. So those, right, you don't need to know because it'll give you those charges right there in the chart. But you do need to recognize that if you see SO3 or SO4, or you see sulfate, and you're like, I don't really recognize those, that you should go check your chart to see if you are given that information for you.
Okay.
Okay, does that help a little bit?
Yeah.
Okay. Right, so in this case, sulfate has a 2- charge. So if it made sodium and sulfate, what charge does sodium have? +1, right? So how many sodium ions would we need in our compound in order to make it balanced? We would need 2, right? We would need Na2 SO4 because we need to balance out that 2 minus charges with the 2 positive charges. That help a little bit?
Yeah.
Okay,
Thank
great.
you.
What other questions?
I do have a question, can you go back to the oxygen and hydrogen, like the atoms and compounds?
Yeah. Um,
Yeah.
This one? Yeah.
So going, okay, so like glycogen, not only those, okay, how you said like 5 times less?
Yep.
That means that like theoretically speaking, if we saw the problem, and it was like how many of oxygen, how many of hydrogen?
Yep.
We would be able to see like this multiplied by 5,
Yep.
depending on how many there are, and get it.
Yes, yep, right, so if
And
you're given a multiple choice question and it's like, oh, right, I know that I have 5 times as many hydrogens as oxygens, and you see, okay, these two numbers is 3 times, then you know that's automatically wrong because it should be a 5-time ratio.
And if the question had said, how many moles of oxygen are in the compound, we would just leave the 6.022 number out.
Yes,
and
yep,
just do the rest of it, right?
yep, so if it was just saying moles, you would just stop after this portion here.
Is there any other form which that question could like be presented?
Not really, I think. I think for the most part, when they're asking about like grams to atoms, it's usually in this setup. Yeah. I think, I guess maybe the only other way I could think of is if you're given a concentration and a volume, right? So then you can find your moles there, and then you can get from moles to atoms that way.
That's
Yep. A little bit, yep, it's more of, like our first clicker question, where it was, right, you have this many you have a molarity of something and this much volume. How many moles of stuff do you have? And then you can solve for it that way.
We go over.
Yep.
Yeah, can you?
So if you're in Dr. Altman's class, I'm not sure if you got this far. But this will just be good for Thursday. So we're given M as concentration. What does M stand for? Molarity. Yep. Right, this is always going to be a concentration unit. What are the units of molarity? Moles over liter. Okay, whenever you see capital M, I want you to always think moles over liter. That'll help you tremendously. Okay, make that connection right now, where capital M is equal to moles over liter. So if we're given a volume of something, we can find how many moles of something we have. Okay, so we're just in the theme of ammonium hydroxide today, right? We have ammonium hydroxide and we have right, so we just said we have a 0.250 molar solution at 5.555 liters. How many moles of ammonium hydroxide do we have? How would we find that? Good, right, so we can multiply molarity by liters. So we could have 0.250 molarity is moles over liter multiplied by 0.555 liters, right? Those are being canceled out, so this liter and liter cancels out. So we end up getting 0.13875 moles of sodium hydroxide. ammonium hydroxide. So then I could ask you, how many grams of ammonium hydroxide do we have? How would we solve that? We would take our and we would use the molar mass and we would end up with 4.86 grams of sodium hydroxide. I'm sorry, ammonium hydroxide. Oh, I keep saying that. What if I asked you for how many hydrogen atoms are there in your ammonium hydroxide? How would we solve that? Yep, right. So we're going to take that first moles in our red and multiply it by how many? Multiply it by what? Multiply it by 5 first, right? Because we're going to say we have right, because every 1 mole of ammonium hydroxide has 5 moles of hydrogen. So that gives us the atoms of hydrogen. Nope, what do we need? We need Avogadro's number. Is 6.02 going to go on the top or bottom? Should go on the top. And again, I don't have the capacity to do that math. Maybe I can try. I think. Did you get 4.06? Yeah. 4.16, okay, close.
Also.
Yep.
It shows up, because like in my calculator, when I do that, it shows up like with E.
Mhm.
And I don't know how to read that.
Yep, so whenever you see E, that just is saying 10 to the power of something. So 6.02 E to the 23, or sorry, E 23 is equal to 6.02 times 10 to the 23. Yep.
In like for the first quiz,
Mhm.
it's gonna include the homeworks, but or questions similar to the homeworks. From what homework to what homework?
It should be your homework that was due Monday. And I think you had homework due the Monday before that.
Okay.
So I think it's those two.
Thank you.
Did that help you with your E?
Yeah,
Yeah.
and then, for our next quiz, is it like you? Like.
No, I think it's based off of so once you finish this one and that's the topic, but right, your unit conversions of moles to grams and everything will probably pop up on every exam or every quiz. And stuff will keep building. So no, it's not cumulative in terms of topics, but your basic information that you're learning right now will probably apply again. Yep. Okay, so just to kind of wrap up this last question. So that purple question I asked you for how many moles of sodium hydroxide or ammonium hydroxide there was, I could have just asked you for how many hydrogen atoms there were right off the bat, and you could have solved it, right? Because we could have just solved for the moles of the ammonium hydroxide and then solved for the atoms of hydrogen right away, right? So it might look daunting to say, okay, I have this concentration, this volume, and I don't know how to get to atoms, but you do. You do. Look at your units and look at your roadmap, and it will definitely help you kind of solve it that way or break it down into steps. Okay, how do I get to here? What do I usually do to get to here? That'll help you a lot as well. Okay, with that, it is 6:30, so I think that that's a good stopping point for today. I will post these extra practice problems for you for next week, or just to do on your own. And if you have any questions, feel free to email me anytime. I'm happy to answer them. And good luck if you haven't taken the quiz yet. Yeah, thank you. Yeah, so I will post them, in the office hours tab. So on, I don't know where this is for me. It should be just a button and I'll house it all there, but it's probably good to show people. So depending on who you're in, but it should be in the same place for both. But this office hours tab, that second one in,
Oh,
all of them, if you just scroll down a little bit, I'll like just kind of populate them where it says the, IA review sessions. It should all be right there.
okay.
And that should pop up with the recording, the practice questions, and then also the answers when I have them ready. Yep.
You ever seen Big Hero 6?
I have not.
You've never seen it?
I have not.
Yeah. You know the girl Honey Lemon? You're just like her. Like,
I'll
like a spinning image of her.
And you're like a chemist.
You're like a chemist.
Yeah.
You have to watch.
have to watch it. Okay.
You have to watch it.
Okay, I'll let you know.
That is good.